All right, folks, we are back with another segment on analytics for decision making. We're going to pick up where we left off in the last segment in discussion of our oil drilling example. Recalling that in the last segment, we considered computing the expected payoff with a perfectly informed signal, meaning we had a geologist that could perfectly identify whether or not we had a wet well, meaning it was a successful drill site, versus a dry well, meaning it was a failure drill site. And another perspective on our geologist's perfect signal is that the geologist does not make any mistakes. He never says there's a wet well that I'm going to give a bad signal to, or the geologist never awards a good signal to a dry well. In fact, if the geologist had done that, and we have very specific names for these types of mistakes with respect to specifically a binary class problem. And it might help to think about the good report as being associated with a positive report and the bad report as being associated really with a negative report, because then we can give some maybe somewhat familiar names to the situations that we are looking at when the geologist makes a mistake. Specifically, in the bottom left situation, where the geologist gives a negative signal, even though it's a good state, should have given a positive but gives a negative. This is an example of a false negative. Okay. Similarly, the zero in the top right would correspond to a situation where they would give a positive report, a good report, to a dry well, to the bad state, to a negative state. And doing so will be again an example of a false positive. Okay, so what we're going to do in a minute is we're going to consider valuing the signal of a geologist, right? Considering, again, that same three-step process for computing option value using our decision tree analysis here. But we're going to change the quality of the geologist. We're going to make the geologist a little bit worse. So instead of 0 false positives, instead of 0 false negatives, they're going to have some. Okay. However, in order to make this situation as comparable as possible, we still want to make sure that we are keeping the relative distribution of successes and failures the same. I still want 20 total wet wells, 80 total dry wells. What we're going to change is, of the 20 wet wells, the geologist is going to get some of those wrong. And of the 80 dry wells, the geologist is going to get some of those wrong. Okay. And we're going to specifically, for this segment, assume that the geologist gets 25% of them wrong. Okay, meaning the geologist is going to be precise 75% of the time. Right. So out of all 20 of those wells, the geologist will get 15 of them right. But the geologist will make that false negative 5 out of the 20 times, 25% of the time. Okay, similarly, the geologist is going to make a false positive also 25% of the time, meaning out of the 80 dry wells, the geologist is going to accidentally give the thumbs up 20 out of 80 times. Okay, now the other thing we want to remember is that we use this historical data to figure out every one of these probabilities in our tree diagram. Every single one we used that table to figure out, utilizing the relative frequency approach, or equivalently, we could have used Bayes' rule for the more advanced student. Now, what we're going to do here is we're going to change the number of false positives and false negatives. I want you to just take a close look at that table. We're going to change them just a little bit. Okay, notice in the W column, there's still a total of 20 successful wet wells. I have not changed that. Okay, and in the D column, there are still a total of 80 failures, dry wells. I have not changed that. The only thing I've changed is how good the geologist is at identifying them. I said out of the 20 wet wells, the geologist only gets it right 75% of the time, right? Meaning gets it wrong 25% of the time. Okay? Same thing for the dry wells. Gets it wrong a quarter of the time. A quarter of 80 is those 20 false positives that we're seeing. Okay, note that once we make this change here, we no longer have a perfectly informed geologist. We don't have a perfect signal anymore. We are specifically now dealing with a situation where we have signal imperfection. Okay, and we're going to now have to recompute every single one of those red and blue probabilities that we had a moment ago on the screen. Okay, using the new version of our data, which is consistent again with this geologist being precise 75% of the time, meaning they make these mistakes 25% of the time, right? 5 false negatives, 20 false positives. Okay. So we should be able to look and condition on the events good and bad, just like we had done with the perfect signal. Okay, but first take note that there are a total of 35 good signals. Okay, 35. How many of them involve the successful drill site, the wet well? 15 out of the 35. Okay, which means 20 out of the 35 involved the dry well. Okay, so we should hopefully be able to look over here and see that, okay, well, this makes sense. 15 out of the 35 good signals involved the wet well, 20 out of the 35 involved the dry well. And we can make, again, a very similar argument with respect to what happens following a bad signal realization. How many total bad signal realizations are there? There are 65. How many of them involve a dry well? Well, 60 out of the 65 involve the dry well. Only 5 out of the 65 involve the success, right? The wet well. Okay, so we are able to, again, using the same relative frequency approach, or again, Bayes' rule for the advanced reader, okay, we're able to recover these forecast accuracies, which again are conditional probabilities, conditioning on the signal realization, either good report from the geologist or bad report from the geologist, to get those posterior probabilities at the tail ends of the tree. Okay, the other probabilities you recall we could compute are the unconditional probabilities of observing the good and the bad signals themselves, right? There's a total of, we said, 35 good signals out of 100, which means the other 65 out of 100 are bad signals. And again, we can simplify those probabilities analogously. The approach we're going to take from here is exactly the same as the approach we took in the previous segment with perfect information, just the probabilities are slightly different now. But we want to compute the expected payoffs conditional on each signal realization. And for each realization, we want to figure out what are the optimal actions. And to figure that out, we need to compute the expected payoffs working our way backwards from the end of the tree towards the beginning, in thinking about the value of the signal itself. Okay, so let's assume here that we've observed a good signal, okay, meaning we are on the top branch of our tree. Observed a good signal. Okay, if that's the case, 3/7 of the time we'll hit a wet well, 4/7 we hit a dry well. That gives us an expected payoff of $10 million if we were to invest following a good signal. And since that is greater than 0, our optimal action is still to invest following a good signal realization. Okay, so given that good signal, that put us here, and we just said our optimal action was to invest. We would never stay out following the good signal realization. Okay, following a bad signal realization. Okay, that puts us on that bottom branch, which means we would get 30 with 1 out of 13 chance, -5 with 12 out of 13 chance. That would yield a negative expected payoff of roughly minus $2.3 million. And since that's smaller than 0, we would always rather stay out and take that certain payoff of 0 if we ever reached that decision node following a bad report. So again, we can really start to simplify our tree here. And we can compute, again, the expected profit from using the signal, which is step 2 in our process of figuring out the value, right? The option value of this information. So again, it was always optimal to drill following a good signal. When we did that, we got a $10 million payoff. And following a bad signal realization, a bad report from our geologist, we said we're going to stay out. If we stay out, what do we get? We guarantee ourselves a payoff of 0. So we can reduce this tree even further and compute the expected profit using the information just as we had done in the past segments. And here we are. So to compute the expected profit from using the information, we want to weight the $10 payoff by 7/20 and the $0 payoff by 13/20. The expected profit from using the information then comes out to right around $3.5 million. Okay, recall again from a few segments ago that the profit on average without the geologist, with no information, that's what we were referring to this as, was $2 million. Okay, so the value of this imperfect signal, you should note it's not as high as the value of the perfect signal. Okay, but we compute it the same way. The methodology, the steps we're using is exactly the same. Okay, by how much did the information, albeit imperfect, cause our average payoff to go up? And the answer here is the value of that signal is now $1.5 million. Okay, note, compared to last segment when we computed the value of the perfect signal, this is significantly lower. With a perfectly informed geologist, right, our geologist got it wrong 25% of the time, was only 75% precise. Okay, our perfectly informed geologist, his signal was worth around 4 million. Right? That was the maximum value of that signal, it was exactly $4 million. Okay, so we were able to compute the value of a perfectly informed signal in the last segment. We now looked at perturbing that, changing that relative frequency data, where we didn't change the frequency of oil in the ground. We just changed how good that geologist was at identifying it being there or not. And we saw that despite the signal being imperfect, it was still valuable. In the next segment, we're going to work through, again, the same example. We're going to make our geologist even worse. In fact, we'll make him just a coin flip. He gets it right half the time, he gets it wrong half the time. And we're going to work the same example and see that in this case, the geologist signal is not valuable to us at all. And we'll also see that it doesn't cause our actions to change relative to what we would have done in the absence of geologist information. So we will pick up there, and I will see you then.